Welcome, or hopefully welcome back to the Reliability Matters podcast. For those of you who are counting, this is episode number 150. It's been said there are three types of lies: lies, damned lies, and statistics. Statistics at its core is the science of making sense of data, from predicting trends and making informed decisions to ensuring quality control and optimizing processes. The applications of statistics are vast and varied. In the electronic assembly industry, where precision and reliability are paramount, statistical techniques become indispensable tools for engineers, manufacturers, and quality assurance professionals alike. Join us as we unravel the complex yet captivating connections between statistics and the truth. We'll delve into real-world case studies and uncover the statistical principles that ensure the decisions we make every day are based on facts, accurate data, and accurate statistics. In today's episode, we're also going to tackle some common myths associated with statistics and shed light on how misinterpretation of data can lead to false conclusions. Many people think of statistics as infallible and a definitive answer to every question posed by data. However, this really couldn't be farther from the truth. Statistics is a powerful tool, but its effectiveness hinges on proper application and interpretation. We'll discuss myths such as correlation equals causation, where the mere relationship between two variables is often mistaken for one causing the other. We'll also address the misconception that a larger sample size always guarantees accurate results, and how ignoring the context or the source of data can lead to misleading outcomes. Moreover, we'll explore real-world examples where statistical missteps have led to costly errors and how these pitfalls can be avoided through rigorous analysis and critical thinking. By understanding these common misconceptions and learning how to approach data critically, you'll be better equipped to harness the true power of statistics. My guest today is Aaron Brown. Aaron teaches statistics at New York University and at the University of California at San Diego, and he writes regular columns for Bloomberg and Wilmot. In the late 1980s and early 1990s, he was a key participant in developing modern financial risk management and one of the original developers of value at risk. He also helped develop the rules that eventually became known as Basel II. Aaron holds an MBA in finance and statistics from the University of Chicago and a bachelor's in applied mathematics from Harvard. And there is a 100% chance I'll speak with Aaron when I return in just a moment.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome, Aaron. Thanks for agreeing to be my guest today.
Thanks for having me, Mike.
I'm looking forward to this conversation. There's a 100% chance I'm looking forward to this conversation. As a statistician,
Correct.
if your social circle, I assume they know you're a statistician and mathematician. Are there statistician jokes that you just get tired of hearing? Or is it such a unique profession that
I would say no. Most of the statistics jokes are actually true, are useful. Like the drunk who's looking under a streetlight for his keys because the light is better than the alley where he dropped them. The statistician who drowned trying to cross a river that was 3 feet deep on average. I mean, these are all important statistical principles that we tell, what professors tell. I don't know too many kind of anti-statistics jokes. Probably are some, and probably I'd be unhappy to hear them.
Well, not like lawyer jokes, right? Where there's good and really, really awful lawyer jokes. I've always been a skeptic when it comes to statistics, because just as a consumer, not as a statistician, just as a consumer, it's sometimes very easy to go, yeah, right. And I have this reasonability effect. Is it reasonable? And if it's not reasonable, then my critical, cynical mind kind of takes over. I remember years and years and years ago, probably when I was a young man, there were a lot of commercials running for a particular brand of chewing gum, and it was 4 out of 5 dentists recommend this brand of chewing gum for their patients who chew gum. And two things came to mind whenever I heard that. One was 4 out of 5 dentists. They probably interviewed 5 dentists, favorable to this chewing gum company. And second, I'm really interested what that one dentist had to think. If it was 4 out of 5 and one dentist said, nope, I do not agree with that, I'm really more interested in what that person has to say. It was I kind of got the back end of the statistic rather than the primary end of the statistic, if that makes sense. Then the second thing that
you were thinking absolutely correctly, and there are two different questions there. The first question, how many dentists did they ask? That's
Right.
kind of a pure technical statistical question. That's where a statistician can help you. How many dentists do you have to ask to really know what percentage recommend sugarless gum? The second one, with any statistic, a statistic is a tiny part of the argument. You got to think, what's really going on here? Why does a dentist think you should chew chewing gum? And so on. So your skepticism is absolutely the right way to approach statistics. And we can start with the simple ones like the 4 out of 5 dentists recommend sugarless gum.
Yeah. And the other mainstream commercial that I see regularly, and I've seen it for decades and I still see it today, are from car manufacturers. And they use a company called J.D. Power and Associates. And they get awards from J.D. Power and Associates. And it's basically, I'm just making the hypothetical. The Ford Mach-E was voted number 1 in customer satisfaction by J.D. Power and Associates. And then I go right to the fine print because they're a big company. They have to have, there's certain rules and accuracy in advertising. So I read the fine print, and it's always something to the effect of, based on polls taken between this date and this date, very narrow date, with drivers ages 25 to 29, it basically a very well-defined demographic that digs those types of cars, or whatever the case may be. It wasn't just like a random sampling of 10,000 people on a New York street corner. It was pretty curated. And given the fact that every major car company all has awards by the same company, J.D. Power, tells me that this company is in the business of providing, in air quotes, accurate statistics. And I don't think they're lies. I think they're highly curated statistics to achieve the desired result. But before we go down that road, because we're right on the edge of going down that rabbit hole, let me just begin with asking you about how you got into the world of statistics and mathematics, because I think there's a correlation. There's a direct connection between statistics and mathematics. What interested you in that professional career and that interest in general?
Okay, well, this is the story of 4 mentors, 4 men who, all men, although people who pulled me in this direction. And to start out, when I was a kid, we had these things called newspapers, and the newspapers had all kinds of big headlines and stories about the world on the front, and in the back they had a bunch of numbers. They had farm prices, they had baseball box scores, they had stock market, whatever, all these numbers. I always read from the back to the front. I loved the numbers. I loved seeing, figuring out patterns. The numbers spoke to me. And as I got to the front, it was like, oh, nonsense. Like, who really cares about this stuff? Do these people really know what they're talking about? And I feel like I'm vindicated because today, if you go back and take a newspaper from the 1960s, the headlines at the front page will seem silly, stuff that didn't matter or that they deeply misunderstood. They forgot about the next day. Whereas the stuff in the back, people still type those numbers into computers and use them for making decisions. So I started studying statistics, and I was turned off because it was all this, mathematical things to kind of torture data to tell you what it wanted. And when I got to college, I met a guy named John Tukey, who's a famous statistician. And he told me, you're right, the statistics is all wrong. What you want to do is exploratory data analysis. You want to let the data speak to you. You don't need fancy mathematics. You do cross-tabulation tables. You do plots. You look for patterns. And this was a big revelation to me that my approach to numbers that I come up with on my own was the right way to get to truth. The next thing I did is, as I was looking at these numbers, it occurred to me you can make money with some of these things. And I got very much into gambling. And I worked with people who were betting on horses. All of this is, some rows that my parents would never accepted it. And I was much too young to gamble, but I advised some horse players and got a portion of their winnings. And I became a very successful poker player. And I came across a book by a guy named Ed Thorpe, mathematics professor who invented blackjack card counting and also beat all of the other casino games. And I got to know Ed pretty well. And this was very important because when you're gambling, people aren't paying you money because you're clever or they like you or you played the faculty politics right. They're trying their hardest not to give you money. And if your methods work for this, then maybe they have a chance of working in the real world. Too many statisticians never test their methods, in something as rigorous as gambling. When you're gambling, you can get 100 independent trials of your idea in an hour. If you're doing something like making economic projections, maybe after 5 years, you kind of halfway know whether your prediction was good or not. So, this constant reinforcement and objective reinforcement is very important. But too many statisticians never gamble. The third one was I get to Harvard, and I was really excited about going to Harvard because there were all these people I had read who did fascinating work, and I wanted to take their courses. And so I pick out my first year courses, and I picked 6 courses, and I take them to my advisor. My advisor says, you can't take these courses. They're not freshman courses, but some of them are graduate courses, and the prerequisites, and you can't take 6 courses. And he refused to sign my card. So I thought about it and I read the rules. And the rules didn't say you had to get your advisor to sign your card. You had to get any faculty member to sign your card. So I went to a guy named Harrison White, who, by the way, unfortunately died about 2 months ago. Very sad. But Harrison White, he's a leading quantitative sociologist. And he said, and I said to him, hey, I want to take your course, but my advisor won't sign the card. And he said, well, no undergraduate ever asked me to sign a card before. I said, well, I don't care. The rules say if you sign it, I can take the course. And he said, well, of course you should take the courses you want to take. Why would anybody disagree? So he signed it. And I took his seminar for 4 years. And some of the smartest people and most interesting thinkers in the world, went through that course. And what he taught me was you understand things by looking at the mistakes. You don't start out by thinking everything works right. You find out, if you want to understand language, you look at the grammatical mistakes people make. If you want to understand the brain, look at the mistakes people, look at optical illusions, look at the things. If you want to understand, society, look at the things that go wrong. If you look at the stuff that goes right, you come up with these simple models where everything's rational and nice and simple. And then finally, there was a guy at Harvard, W.V.O. Quine, an important philosopher and logician, and I took his course, and I pestered him with all these questions because he was a really smart guy. And finally, he got tired. He said, 10 years ago, I had a student who asked these same questions, and now he's teaching at MIT. Go talk to him. And that was Fisher Black, who was famous for the Black-Scholes option pricing model, but I had no idea at the time. He would have gotten the Nobel Prize in 1995 had he lived, but unfortunately he died. He died young. And he had no students because nobody took him seriously. Nobody believed what he said. And so I sort of became his only student, although I never actually took a course from him. And he wrote a book called Exploring General Equilibrium. And again, he had the same idea. You don't run into an economy and look at what it's doing right and come up with some simple rule. You explore it, and you look at the things that go wrong and try and figure out why they're going wrong. So these are the people who pulled me in, and none of them are to blame for all of my mistakes and errors. I can't say that. But everything I do that I believe and I think has some DNA from those poor people.
Excellent. You talked about illusions. You referenced the phrase illusions, and it just made me think that I don't think it's fair to say that statisticians and magicians have similar qualities, because a true statistician knows how to get to the truth. But manipulators of data, let's call them that, that provide that draw untruthful conclusions from a pile of data. Put it that way. I think there's a lot of similarities between magicians. It's sleight of hand.
Well, I tell you, the big similarity is distraction, right? So, magician does something with his right hand to take your attention while his left hand is palming the object, or whatever.
Pay no attention to the data over here. Look at this data.
Well, the statistician, they'll tell you, I rejected the null hypothesis with a 5% significance. And they focus your attention on the 5% significance, which is almost totally irrelevant to the claim. But it seems to give it this imprimatur of scientific inimitability. The purpose of most statistics is to distract.
Yeah. Pay no attention to the shiny object in the corner. Okay, we talked about your history with statistics. Let's talk about the history of statistics. I read some work you did that talked about the genesis of statistics, where in our ancient world statistics came from. I found that fascinating because it morphed over the years, and it kind of explains where we are today. It puts it into better context. Run me down that historical road of where statistics came from, what society propagated the idea of statistics, and its evolution to today.
Okay, so here's the 2-minute version of 2,000 years of history.
There we go.
Mathematical probability is traced to a series of letters between Pascal and Blaise Pascal and Pierre Fermat, two French mathematicians in the 1660s. And the mystery isn't the mystery.
Is that the same Pascal? Sorry to interrupt. Is that the same Pascal that the programming language was named after?
Yes. And Pascal's triangle and Fermat's last theorem, if you're...
Okay, all right.
So these are famous mathematicians. And the mystery is, these guys did advanced mathematics that, math grad students struggle with today. And yet they were completely puzzled over a problem that any high school student could handle. So the mystery isn't that they discovered mathematical probability. The mystery is why it took until the 1660s. And we don't even say, if you go farther back, you don't even find words. Like the word random to Shakespeare meant fast. And later it acquired a connotation of reckless. And only later did it get this idea of uncaused. And the basic reason is that prior to the scientific revolution, everything was caused by the gods. And suddenly science comes along and starts explaining some stuff without gods. And that meant, well, what about the rest, So once people figured out that there was science, things not directly controlled by the gods, they had to ask about the other stuff. So, you understood why the planets orbited the way they did, and you had to ask, well, why did I lose the battle? And it was a different kind of answer. You couldn't get a scientific answer to that. You had to reference random events. So that's a mathematical revolution. It spreads throughout much of the world, certainly most of Europe, in less than a decade. And so it couldn't have been word of mouth or one book or one publication. It had to be something was in the air. Everybody was thinking that, now that we have science, we need something to explain the rest of the world. So we jump forward 100 years and we get the word statistics, which comes to us from the German. And to understand it, you have to parse it as statistics, the study of the state. So you have all these German princes, and they're constantly swapping princedoms, principalities due to marriage or war, contract, whatever. So they owned or controlled all these areas that they'd never met, they never visited. They had idea about. So they sent out people to gather data. Being German, they were systematic. And these people wrote down how many cows are there, how many workers are there, how many farms are there. And on the basis of this, the prince could decide with its advisors, should we conscript a bunch of people and use them as mercenary troops? Should we put more cows here? Should we tell these people to stop growing hay and start growing some cash crop? Whatever. And this is the reason we use the word statistics to mean numbers published by the government. Now, the German statistics people didn't publish theirs. It was secret. They brought it up for the prince. But this was one source of the modern field. Then we switch over. In England, people are doing political economy, and it's just the opposite. These are people outside of government, complete amateurs, ignored by the government, who are doing calculations. They're looking at death registers, they're looking at wheat prices, they're looking at all these kinds of things. They're doing analysis of data, mathematical analysis of data. And this is another thread that kind of got tied in. Then you get the French Revolution, and the French were kind of halfway in between. They understood the English political economy because they'd read this stuff, and they also understood the German statistics. Many of them had been trained in it. And their problem was these were all intellectuals from Paris, and they didn't know anything about France. The country had hundreds of languages, thousands of cheeses, different cultures. But they wanted to rule it, and they wanted to rule it in a scientific way. So they sent out questionnaires to schoolmasters and people in different parts of France, and they said, write down all the stuff that the German statistics people collect. But they had a totally different idea about it. They said, we want to average everything so we can find the average French person, and that's the ideal French person. Everybody should be the average. So we have to know what that average is. And this is where we get the idea that abnormal or deviant are bad. They had the idea that everything should be the mean. And finally, in America, we get this idea of the census. We get the idea of the government sending around and asking all these questions about people, that this is how you do government. So we jump another 100 years, and we get to the late 1800s. And now we're seeing people are using statistics to control people. They're not using them to find truth. They're using it to approve drugs. They're using it to monitor workplace efficiency. They're using it for all these things to control people. And this is what most people think of as statistics today. Not the pursuit of truth, but setting up standards so you can manage people, either a government, a prince, a company, a scientific researcher who's has staff who are looking at photographs or polling people or so on. And only in the 100 years after that, we get the invention of Bayesian methods, we get exploratory data analysis, we get all the kind of statistics I like. And that's what I'd like to talk about today. I'd like people to kind of forget about the late 18th century, second industrial revolution, scientific data torturing statistics, and think about the pursuit of truth and exploration and letting data talk to you.
I love that, the way you put it, the pursuit of truth. Data are, to me, to a layman, data are the ingredients of truth. Data is what data is. The manipulation of the data is where we go sideways, where governments control people and pharmaceutical companies get their drugs approved, and people buy certain cars over others because they believe that they'll be more satisfied. That's the kind of the dark side of that. But raw data is raw data. It is what it is. If I'm basing a decision, I own a company, a manufacturing company within the electronic assembly industry. And if I'm trying to make a decision off of published statistics, I see claims from advertisers. And in my world, most of the stats I hear have something to do with someone wanting to sell me something. Maybe we've morphed from government control of people to Fortune 500 control of customers and consumers. But what are some of the useful questions I need to ask to evaluate any statistical claim? In other words, when there are some key factors or techniques used, what are some of the key factors and techniques used to vet the efficacy and the reliability of a statistical claim? Most of us are not blessed to be statisticians. So give us mere mortals some advice on where do we start?
Okay. Well, this is going to be easier with an example, but it applies to any statistical claim.
Sure.
So you read, clickbait on the internet, drink red wine to live longer. Okay. You see that kind of thing all the time. Then you say, well, I'm a skeptic, right? I'm going to say, what's the study? And you look at the study. The study said, we rejected the null hypothesis that red wine drinkers live the same or shorter than non-red wine drinkers at the 5% level. So here's where the distraction comes in, right? That 5% level. That is the last thing you should be thinking about. The statistics are the tail end of an argument. The person is making a logical argument from data. And the first question is, do I buy the argument? If you don't buy the argument, you don't care what significance is attached to it. It's wrong. It doesn't matter. And so you see, well, what was the study? Well, the study was they looked at a bunch of people and they found that the people who drank red wine lived longer. That's fair enough, but you're going to ask a lot of questions. Like, did they look at death certificates and then determine if the people had drunk red wine, in which case maybe some of the non-red wine drinkers are still alive? Did they look at red wine drinkers and find out when they lived? Well, how did they find them? What about kids, right? A lot of people die in the first few days of life, and clearly those people are not red wine drinkers. And a couple of zeros can really bring down an average of everybody else. Did they adjust? Maybe red wine drinkers are richer. Maybe red wine drinkers do other healthful things. But so you read it, and maybe they did a good job, maybe they didn't, and this is what you should be thinking about. Don't look at that 5%. That's just crazy. How they did the statistics don't matter. Just look at how did they select their sample? Did they adjust and control for, things that should matter? Now, if you don't like the logical argument, forget it. The statistics don't matter. If you buy the logical argument, say, okay, they did a good job and they got a good sample, and it really does look like red wine drinkers live significantly longer than non-red wine drinkers. Now you want to ask the statistical question, which is, was your sample too small so that maybe this was just random luck? And maybe you just got, 5 coin flips of heads in a row. And that's what the 5% means. The 5% says, it probably wasn't just random chance. If there was data we got would occur less than one time in 20 if there were really no difference between the age of deaths. So that's a nice bit of confirmation. Given that you bought the general logical argument, almost all the mistakes in statistics are not that people computed that 5% wrong, or not that they did bad statistics. It's that they did good statistics on a bad logical argument.
Yeah, very interesting. To me, the real impact is you have to look at the statistical sample, as you mentioned. The point you made with infant mortality was obviously quite valid, and it is. Zeros can totally affect the average of a statistic. I think it's also helpful, or I should actually phrase this as a question. Do you think it's also helpful to look at if it's even possible, who's generating these statistics? If Mondavi wine or Gallo wine was the sponsor of the study to determine wine makes you live longer, to me that automatically casts a bit of a dark cloud over the veracity of the conclusions of those statistics. Is it easy? Is it sometimes that transparent?
Yes, that's certainly true, but I think people make too much of it. Unless you think they're lying, unless you think that they actually, didn't get the data they reported, or you think that they, somehow cherry picked it, like they they took a sample of 10,000, then picked the sample of 1,000 to generate their view. So if you believe, if you're worried about gross malfeasance, that's an issue. And certainly there are lots of partisan organizations that engage in gross malfeasance. But if you read the paper and it sounds reasonable, and
a reasonability test, yes.
Yeah, I don't care too much about who funded it. If you're, it's lots of good work. And look, generally speaking, to put serious money into investigating something, you kind of have to have some interest in the outcome, right? So yeah, Mondavi is going to study, how red wine drinkers do, but that doesn't mean that they're going to. And what is probably true is if they find a bad result, they wonly publish it. So
true, and there's no sin in that, right? Right.
Well, it's personally, I would love it if everything got published, positive and negative results both. But anyway, so
make it more credible.
While you should certainly look at it, I think it's less important. If you look at organizations, you find there are organizations that are highly partisan, but generally put out reliable statistics, and there are institutions that put out only things that wildly support their positions and are frequently debunked. So it's pretty easy to tell, who's really doing it and who isn't.
I think these days, if it comes from a political organization on either side, I'm a huge skeptic of that.
I'm going to push back a little on that. Brookings Institution, Heritage Foundation, they're kind of on opposite sides of the politics, but they don't publish out and out lies. They,
Oh no, I meant more political candidates. I didn't mean to
political.
I didn't mean to impugn the think tanks.
I give them credit if they can even make an intelligible statement, much less.
But yeah, they probably can't pronounce the word statistic. At least not our two candidates. But we won't go down that. That's a deep rabbit hole. Let's talk about the derivation of statistics. How are statistical measurements like the mean, the median, and the mode derived from raw data? What are some of the mechanics of it? Give us a moment of a statistician's life here.
Yeah. So this is the field of descriptive statistics, and descriptive statistics is much less controversial than inferential statistics. So we've been talking about inferential. So descriptive statistics is a simple problem. You got a bunch of data and you have to simplify it. So, I teach. I get, a lot of kids in my class are mathematically minded. In fact, all of them are mathematically minded. And, a question I get is, I'm thinking about going into engineering or finance. And, there are about 1 million practicing engineers in the country, and there are about 1 million financial analysts. And they say, well, which one's going to make me more money? And that's one thing you want to think about. And you say, well, Bureau of Labor Statistics tracks this, and they tell me that the average financial analyst makes $125,000 a year, and the average engineer makes $110,000. So, you might say you're going to make more as a financial analyst. But when you look more closely, you find that the median engineer makes about $100,000, and the median financial analyst makes about $85,000. So now you know a little more. You say, okay, there's some really rich financial analysts. There are really some high-income financial analysts who are pulling up the average. But if I just think I'm going to be average in the field, then I'm going to make more money as an average engineer than as an average financial analyst. And the mode, the engineering mode is higher, the engineering mode is 75 to 80, and the financial analyst mode is 55 to 60. So most financial analysts make less than most engineers. And with those three numbers, you got a pretty good idea. I mean, I could show you a million, well, I can't show you, but Bureau of Labor Statistics could show you a few thousand people they polled to get these estimates. And you could look at every number, but you wouldn't know a whole lot more. These three numbers have pretty well described the income distribution from the two fields.
Interesting. So regarding the data collection, the collection of all the data, what are some of the best practices for collecting data to ensure that statistics are derived, are accurate and reliable? And the reason I frame it that question that way is, in our industry, in the manufacturing industry, the big push right now is Industry 4.0, which is basically the connectivity of machine to machine and machine to cloud and the collection of data. Ever since memory the cost of memory got really cheap, like super cheap, and computing power has exploded. It makes the collection of data easy and inexpensive. So now we have this big data world in our industry, and probably every industry is affected by that. Now it's not a question of how much data do we collect. We just collect everything. Now what do we do with all this data? So walk me through the data collection best practices and again, to restate the question, how to ensure that statistics that are derived from all that big data are the right data points, and that to produce a statistically reliable, accurate result.
Yeah, okay. So it obviously very context dependent. So the best thing is to have all the data, right? So if I want to know about, U.S. population, if I have data for every single person, and then things become a problem of descriptive statistics. How do you summarize all of this into getting useful information? But most of the time, we don't get all the data. So I would say the first important rule, best practice, is to think about the data you don't have. For example, there's survivorship bias. For a lot of studies, we're not getting the people who died. We're not getting the companies that went out of business. And these are very important to our analysis. Are we missing the underground economy? 15% of Americans are working in the underground economy and are missing in most, payroll data, employment data, things like that, and including those people should be very important. So you can't get the whole. Typically, you can't get all the data, but you should know what is missing. Second, most of the time we're going to be missing data even from the things we cover. Maybe we have only a poll. We have what 2,000 voters think. We don't have every single voter. We have, one item in 1,000 from our assembly line we pull for quality control. We don't pull every single item and test its quality and so on. Let's start with simple random sampling. If you have a simple random sample where everything in the population has equal probability of being selected, that's kind of the classical thing statisticians like. But they like it because it's simple, not necessarily because it's good. Now, there are many worse things you can do. An awful lot of the samples you see data from, they're self-selected. You put out a question on the internet, and anybody who wants to answer, they're convenient samples, right? Psychology professors love to sample their psychology students because it's easy, it's cheap. These are terrible. Snowball sampling. You find one person, and then you get that person to recommend new people. So all of these are terrible ways to sample, and basically most studies from them are at best indicative and suggestive, and then usually worthless. So simple random's kind of in the middle. There are sophisticated sampling ways, stratified sampling, importance sampling, cluster sampling. I'm not going to go into all the technical details, but if you're really searching for truth, you're going to seek out the data that's important rather than just sampling everything randomly. A good story about this is from my mentor, John Tukey. In the 1950s, there was something called the Kinsey Report, which was really the first serious study of human sexuality, and totally path-breaking, completely changed the field. And Kinsey was kind of an odd guy, and he recruited a sample. He went to prisons to get child molesters. He went to gay bars. He went to S&M clubs because he wanted to find people who would talk about the sexual practices. And he took them back to his laboratory and had sex with them and filmed them and whatever. So he's kind of a
research.
Well, he's a controversial guy. But frankly, if you're going to study sexuality, you ought to have a little sex. I don't know. You ought to. In most fields, we would think this was normal, right? But in sexuality, there's so many taboos.
Right. Yeah. Little stigmas here and there. Yeah.
Anyway, so Tukey famously said that he would prefer a random sample of 5 individuals to, Kinsey's thousands of in-depth interviews. And Tukey was dead wrong. This is kind of the worship of random samples that even smart guys like Tukey fall into. If you want to study human sexuality, you got to go out and you find the deviants, the people who don't do the socially approved stuff. Just like, Harrison White's idea, you study the mistakes. And by the way, I am not suggesting that all sexual deviants have made a mistake.
Right. But you have to get both. You have to get the extreme ends of the spectrum in order to contextualize all the data, right?
The person who grows up heterosexual, gets married, never cheats, whatever. They don't teach you much about human sexuality. They're just kind of doing what they're supposed to do. The people who can override their urges aren't telling you much about what those urges are. So this is very important. So the kinds of sampling where you can find the things that teach you the most, that to me is best practice.
Yeah, it goes back to the example I said earlier, which is, I'm more interested in the one dentist who doesn't recommend sugarless gum. I'd like to see a survey of all the people who were against it to find out what the commonalities are there and compare that result to the people who were for it and find out what the, hierarchy of decisions was and what their sensitivities were to certain things and understand their decision-making process rather than just, yeah, I like this. Yeah, I don't like that. I'd like to get it deeper into that. So it is important to look at, on any subject, deep down into the extremes. Now, how do we contextualize that for the electronics industry? I love your point of collect all the data. Data's good. And in our world, we don't really have, to me, it's like the difference between fishing with a net and fishing with a hook. In the world of data collection, you want a net. You want a troll with a big, wide net because you don't know the statistical significance of any data point until you analyze it. And the data we don't analyze, to me, is statistically important. The fact that the absence of certain data, to me, is statistically relevant to discerning whether that data is accurate or applicable. Speaking of accurate and applicable, you'd mentioned that most statisticians and the people who compile statistics are probably not intentionally trying to mislead. They may be inadvertently misleading. They may, through omission of certain data points and all that. But how can statistics be manipulated or misrepresented, either intentionally or unintentionally? And I think that the opinion is it's rather unintentional or not the result of malfeasance. Maybe partisan if you're trying to promote a particular point of view or a brand over others. But what are the most common manipulation techniques of statistics to produce a desired result or to find a desired result within the collection of data?
Yeah, and there is plenty of deliberate malfeasance, and there's also plenty of people who never learned enough to do it right, and know they're doing it wrong because they don't know how to do it right. But my claim was that most of that is not in the statistics themselves; it is in the data. Right? You just forget, erase, or change inconvenient points. You word things in such a way. For example, a very common thing: you're partisan. You want to find a certain result. You want to think, okay, all Americans want Medicare for all. You don't ask them, are you for Medicare for all? You ask them something like, well, shouldn't every sick American get treatment? And you find, okay, 90% of people say yes. And you publish that as 90% of Americans support Medicare for all. Or if you wanted it the other way, you would say, should the government prohibit people from paying for their own health care or something like that? I mean, there are ways to do it. There's actually a famous example in polling where Gallup did this actually just to test. They asked, this is back in the Vietnam War days, they said, should the U.S. send American troops to Vietnam, and should the government send American boys to Vietnam? And of course, I don't know, 70% of people said yes, they should send troops, and only 30% said they should send boys. So this is the kind of thing people do. People just make up data. People put out a survey on the internet that's really only directed at their own members. Only their own members see it. So the NRA sends out to all NRA members, do you think we should ban all handguns? And only 2% of people say yes. So these are the kinds of things people do. But given their data, the mathematical way they analyze it is typically not done wrong. So they rig everything through the data. So what you've got to look at is how are the data collected, exactly what question did people ask, how did they select respondents, things like that. That's where most of the problem gets. Now, where you do get malfeasance on the statistics is what we call p-hacking in academic literature. So academics need publications for promotion, for hiring, for career advancement, for grants. To get a publication, you need a p-value of 5%. We have to worry about what that means, just you need to get it. And so people do whatever they have to do to get it. And because very few researchers can get the number of high-quality publications that are demanded by career purposes. So even the best of them usually have to resort to some low-quality publications. And the easiest way to get a low-quality publication is to p-hack it. So you run your study, and it gets the result you want, but it's not convincing enough statistically. It's got what we call, say, a p-value of 8%, and you need under 5 to get published. So all kinds of things you can do to get it under 5%, and then you publish it, which it means that a p-value of 5% just doesn't mean anything because it's so easy to fake.
Interesting. I read of in preparing for this interview today, I was reading an article, and I wish I had the citation, but it was about a person or an entity, I'm not sure which, that wanted to make a point. So they wrote and it was on the subject of p-hacking, and they wrote a study based on the claim that eating chocolate makes you live longer, much like the wine claim. And then they had it published in a peer review journal. I don't know which one. The press picked up on it and started doing reports that certain types of chocolate, probably dark chocolate, because that's the one I remember, was good for your health. And studies show that people who regularly eat this form of chocolate are statistically shown to live longer. And it was widely reported in the press. And then the chocolate companies all picked up on it. And the whole thing was a stunt. It was to make a greater point that, be careful what you read. And it was they basically dropped this little, time-fused grenade down the hole and waited for it to explode. And it did. And I don't think even to this day, I know that I still remember studies and believe that dark chocolate, whenever I don't enjoy a lot of sweets, but when I do, it's always very cold dark chocolate I keep in the freezer. And I just find that satisfying. And then to relieve my guilt, I go, what? It actually technically is pretty good for you, at least in moderation. I think I was a victim of that stunt, and the fact that chocolate is good for you was the resonance of that message was far louder than the subsequent, well, this was all a stunt. This was all to prove a point. And that got forgotten. And the false results are what people still remember today.
Yeah. There've actually been several studies, several people have done this where they picked a completely absurd hypothesis. And by the way, that was probably the most reasonable hypothesis of all the ones people test. There's a famous one of somebody who said people who listen to the Beatles song "When I'm 64" live longer. And whatever. But here's the thing. They use absolutely standard approved statistical methods. And their point is these approved statistical methods are worthless because you could easily prove ridiculous hypotheses with them. Now, most of them are careful to pick things so ridiculous that even the journalists are sometimes, skeptical. At least, the CNN, New York Times, Washington Post journalists. These studies may get written up in the National Enquirer or some other site. The trouble with the chocolates are good for you study was it was reasonable enough that journalists picked it up, and journalists pick up all sorts of absurd claims, all sorts of these clickbaity things. In fact, and this because if you just think back on the things that have popped up on sidebars or something over the last year, virtually all of those claims were forgotten a week later.
Yeah. And they come back. It's kind of like fashion.
Yeah,
they come back again. They're cyclical too. We forget
but they
about
are
it.
All based on studies that are done according to statistical practice. So this is not a question of people lying or cheating. This is people doing it, playing it by the rules, but finding support for absurd conclusions.
To me, the most shocking thing about the When I'm 64 example that you gave wasn't the statistics that were drawn from it or the conclusions from the statistics that were drawn from it. It was the fact that the lead singer of that song is now about 80. Paul McCartney. I turned 64 in November, so I think that'll be well played in my household, probably for the entire month of November. As we wrap up, Aaron, let's discuss some of the ethical aspects of statistics for a moment. What ethical considerations should statisticians, should your posse, keep in mind when analyzing and presenting data? If you're tasked with a project, what are the ethical considerations any statistician should consider when taking on a project?
There's a very important dichotomy we've got to put in here. So many statisticians are like lawyers. They're hired to make a case. So, if you're an expert witness in a trial, they don't call you up and say, what's your opinion about whether this drug caused cancer? They say, we need you to bolster our case to present the scientific case for the drug was safe or the scientific case for the drug caused the cancer. And I don't think there's anything ethical about being a lawyer. If somebody wants to know what is the scientific evidence for something or what is the best case that can be made for something, there's nothing unethical about answering that question. And many experts have, auditors, accountants, engineers for that matter. There are engineers who are, the bridge was safe. No, the bridge was not safe. Well, you're not being hired as an impartial person giving your best judgment. You're hired to assemble all the evidence on one side or the other. But even so, that doesn't mean there's no ethic. You don't put in false data. You don't misrepresent things. You don't do bad statistics. You just collect the best argument you can for your side. But then there are many other statisticians who are hired to find the truth. They're not hired. They may be, the people who hire them may want them to be on one side or the other, but they are representing themselves as unbiased experts, coming to the best conclusion possible. And for all of these people, whichever you're doing, so obviously the second group has a bigger ethical objection to present both sides, to present the whole picture. But whatever you do, all data and code should be made publicly available. To me, there is no excuse. When I spend a lot of time trying to replicate results from academic papers, and some authors put their data and code up for public. Others, you call them up and they send you the data with no problem. The people who refuse to divulge their data, in my experience, are almost always junk studies, almost always, and often it's the problem is they don't have the data they say they did. Other problems, there are other issues as well. And then other than that, you use your best judgment and you say exactly what you did and why you did it. That includes or should include things you investigated but didn't find. So a very common thing you can do is in fact, here's a standard study in nutrition, which is one of the reasons nutrition is such a terrible field. You send a questionnaire to thousands of people and you ask them hundreds of things. Do you eat carrots? Do you ride a bicycle? Do you do this? Do you do that? And then you do a statistical study to see which of these things are correlated with, say, heart disease. Well, with hundreds of things you study, and by the way, they use combinations, so you get millions of people who eat carrots and ride bicycles on Thursday. You can always find these statistically significant results because you don't tell people how many different things you tested. If you test 1 million false hypotheses at the 5% level, you're going to get 50,000 false positives. So these are the kind of things, this sort of disclosure. But I think if you fully disclose what you did, fully disclose your data, fully disclose your code, and do your best, either your best to present the case on one side if you're being hired for partisan purposes, or your best to present all the data if you're representing truth, I think you've fulfilled your ethical obligation.
Excellent. And last question, Aaron, bust a myth for me. Your favorite myth. We talked about chocolate making you live longer. We talked about drinking wine and chocolate. I could accept those just on face value. But what are some of, maybe historically, it could be in history or it could be modern. What false conclusions have we as a people believed that turned out to be statistically incorrect?
Well, it's hard to. I'm going to pick one. This is actually one of my favorite, a former business partner of mine, and he said it is the myth of efficient government. And what he meant by that is, most people kind of tend to casually assume that, the government kind of does what it says it does. So, the IRS collects the taxes it's supposed to collect. Yeah, yes, there's some cheating, there's mistakes, there's errors, that, the government publishes a statistic that somebody actually gathered that in some reasonable way. And he said, it's just not true. And what's actually going on is completely different from that. And if you kind of assume, if you sort of read a civics textbook and you take the normal view of how things should work, how they might work if one reasonable person was in charge of everything, and then you compare that to how it actually does work, there is zero correlation. There's no connection at all. And it kind of goes back to, I think it's more broad, it's a broader thing. Things do not work the way everybody thinks they work. People's models of the world are radically oversimplified and often wrong. If you want to know how a cellular phone works or a computer works or even how a pencil works, it's a lot more complicated than any one individual could even know.
Yeah, you're absolutely right. The world I work in, the electronics industry, it's deep. There's the consumer view of electronics. You flip a switch, something happens, and then there's 8 million steps behind the curtain that actually make it happen. And various industries, various countries, all these different entities that combine to make a light bulb turn on, or this technology possible. It's definitely rabbit hole kind of stuff. Well, Aaron Brown, you've been extremely generous with your time. Thank you so much for sharing the world of statistics with me and my audience. I think I understand it 8% better than I did before. There's so much to understand, and I appreciate your candor, and I appreciate your examples and your wisdom. And thank you very much for being my guest today. I really appreciate it. I hope we get to meet in person someday.
Thank you, Mike, and thanks to all the listeners.
Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to click the like, subscribe, and bell icons to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. And a special thanks to the Printed Circuit Engineering Association's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks also for your questions and episode suggestions. Please keep them coming. I love to hear from you. Send comments or questions or episode suggestions to Mike at mikeconrad.com. Just remember that's Conrad spelled with a K. To learn more about the Reliability Matters podcast, please visit the Reliability Matters podcast website at where? You guessed it, reliabilitymatterspodcast.com. Once again, thanks for listening or watching. Until next time, stay safe, stay healthy, stay happy, and perhaps more importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.